Hello guys, in today's video we're going to take a look at a special data structure, Quadtree. We'll start by looking at an example. So suppose I have a 2D rectangular space with a bunch of messy points scattered inside. And within this space, we have a small orange rectangular region. What I want to do is to find which points in this whole space exactly lie inside this region. Now, if I don't have any special or particular data structure, I would probably use an array to store the coordinates of all the points here. And what I would have to do is to scan the entire array and compare every single point with the boundaries here to check if they are in there. And now, in this case, if the number of points is very huge, that would be a massive amount of time. So here's what I do instead. So firstly, we divide the big rectangle into 4 smaller ones, right, as you can see here. And then we do this again. And since the tiny cell in the top left corner has more points, so I split that one yet again. At the same time, I will keep track of the parent-child relationship between all these rectangles. Now, when I search for the points inside this orange region, I can use its coordinates to go straight to the upper left area. I can skip these 3 rectangles because they are not intersected with this area, right? And within this subrectangle, we don't need to consider the one on the bottom because they're blank, right? And what we need to consider is this one on the right and this one on the left. So that's the idea behind a quadtree. A quadtree treats the entire space as the root node, and then it just recursively splits the 2 space into 4 quadrants. And each split creates their child spatial nodes unless they are blank, right? In our example, the point objects are associated with the leaf spatial nodes. In other words, only the leaf store points, and the leaves are linked upwards through their parent nodes. So the non-leaf nodes are only used to find the leaves. And so when I want to search for objects with this region, right, I start from the root and descend to the leaves that intersect with this region, and then read the objects stored in these leaves, which is exactly the points in these 2 space, which will be stored in the leaves. So the efficiency lies in the fact that we can completely ignore large parts of the space, which are irrelevant to our query, right? We can skip this area that are irrelevant to our query area. And especially when the points are evenly distributed, this becomes very efficient in time and space, both time and space. And some basic operations and their complexity, right? So for inserting, deleting, or point queries, O log n, right? And the reason is that if each level of the tree, we are zooming in on one of the 4 quadrants, right? So if you are familiar with the binary search, it's just like a 2D version of binary search. So it's definitely a log n. It's definitely a log, no matter what. And for range query, the log n it just comes from how many steps it takes to reach the relevant leaf nodes, just like before. And the k part is special because once you find the relevant leaves, you actually have to return k matching points and outputting k things. So it takes OK times. And we have to keep this form complete, because once the n and k are both large, then the log n will be much smaller than the k. So we have to keep k in this expression. For the worst case, so if the points are clustered in just one tiny area, then the tree just keeps splitting and splitting and only in that one corner. And that means it will turn into a deep, skinny tree, almost like a linked list. At that point, you're basically back to checking every point one by one, which is O time. First, the most map services and GIS are basically almost where the quadtree is mostly widely used. Google Maps or any other map application definitely use the quadtree to do spatial indexing or region-based POI queries. And also in image processing. But in image processing, the quadtree is not used as often as before now, because there are some more advanced algorithm here to do the image compression and segmentation. And it's also used in game development and spatial databases. And this application is actually a part of the GIS, I think. While quadtrees are powerful, they do have some limitations. One key issue is that the performance can degrade significantly when your data is highly clustered, right? And also, it's not ideal for higher dimensional data. This Archie might do better for range search in the higher dimensional area. And it can become unbalanced, wasting space. This is actually a common problem of any kind of tree, right? And rigid splitting, always 4 quadrants, even when not needed. I don't think this is a true problem because we can leave the node. We can just not create a node if it's not needed, right? So it's not a true problem here. So I think it's not ideal for higher dimensional data, or it's not efficient as other tree like KD tree in some more advanced or particular area. So that's the main problem and limitations here. So it's mainly so briefly summarize. It's only depending on your specific use case you may want to explore these alternatives if you need it.